Thank you very much. I actually was looking forward for an afternoon tea before my talk. So unfortunately, I'll just start my talk without the afternoon tea. And thank you so much for still being there, even without the afternoon tea to cheering up. So today, I'm very glad to have the opportunity to share with everyone the research collaboration we've been doing with ICO Solar. Okay. So before I start, as always, just wanted to introduce our center. Our center is called the Australian Center for Advanced Photovoltaics, and it was founded more than 10 years ago, back in 2013. It was mainly hosted in our university, the University of New South Wales, and we received funding from the Australian Agency for Renewable Energy. So even it's hosted in our university, it actually consists of all the universities and research institutes in Australia that are doing solar. So you can see we consist of UNSW, Australian National University, Melbourne University, University of Queensland, CSIRO, Monash University, and Sydney University. And here's our management committee, which the senior researchers managing each institute. I'm currently running the UNSW node. And within our center, we do a variety of research topics from the silicon solar cell, emerging materials, all the way to integrate into tandem device and device to module stability, and all the way to manufacturing and sustainability. Okay, I'll start my technical talk after the promotion of our center. So I'll start my talk by saying we love silicon. It's definitely, no doubt, an excellent material for PV device. It has a perfect band gap, it has a strong absorption, and it's earth abundant, it's non-toxic, it's stable, and it's super efficient. So over the last few decades, we've been seeing this amazing efficiency enhancement for our silicon devices. And with technology transition from aluminum back contact, aluminum BSF cell to PERC cell, TOPCon, heterojunction, and now with BC representing the highest efficient silicon devices, we are really approaching the efficiency limits of the 29.4% efficiency. Because right now, the silicon cell are approaching the efficiency around 28 efficiency. And then the question comes, what comes next? I guess the very obvious answer to everyone is tandem. Of course, it's seems like everyone is working on tandem right now. So tandem structure, I don't need to explain in too much detail. Literally, you just stack a high bandgap material on top of a lower bandgap material, and then with the top cell absorbs the higher energy photons, and then with the bottom cell absorb the rest of the photons. And talking about the tandem, we know it can definitely push the efficiency a bit further, even beyond the 40% efficiency. Apparently, perovskite is the most popular tandem materials so far, and we've seen this rapid emergence of perovskite material in the past decades. But we all know there's still some room for further improvements before the mass production. So we listed 3 S here. So one is the size. So on the very top right-hand side, we are comparing the size of the record silicon cell with the record perovskite cell. So we can see, regardless of size, perovskite still have a long way to go. And also scalability. We know we can fabricate really highly efficient perovskite device in the lab, but how do we translate it to the production line? And the scalability definitely needs to be solved before we go to the mass production phase. And the other thing all of us are super interested in is the stability. So, and we know the stability is the barrier. If we cannot solve the stability issue, then we can't really talking about commercialization. So here's something we really want to play a role in as well. So we know that there's a lot of research papers published about the indoor stability, about the perovskite devices. But what is really interesting is the outdoor performance of the perovskite devices and how do they really perform in this real-world environment. So I guess the PACT Center in Unreal is probably the only one who has doing this comprehensive outdoor testing for perovskite modules. They're doing single junction perovskite modules and also perovskite tandem modules. through their comprehensive study, we can see almost more than 90% of all the mini modules they tested all reached 80% of the original peak efficiency within 1 year's time. So that's a bit disappointing. And another thing I wanted to point out is all the modules they tested are only lab scale modules within the size of this big. But we know in China, there's many manufacturers who are manufacturing large scale, like 0.6 by 1.2 meter perovskite modules. Well, unfortunately, Unreal cannot test those commercial modules because of some political reasons we are all aware of. So luckily, within Australia, we don't have these political constraints so far. We love to collaborate with everyone. So we are starting a new initiative that we are collecting the commercial perovskite modules from all leading manufacturers. And so far, you can see we already mounted 10 commercial perovskite modules on our roof. The bottom line are all commercial perovskite modules, and the top ones are silicon modules. And we believe we are the first one who actually started to testing commercial perovskite modules in the real world. And almost all leading manufacturers are part of the game already. And we promise we wanted to protect your privacy, so all the data will be anonymized. Don't worry, no secret will be leaked. And if you wanted to join the party and be part of this outdoor testing initiative, just feel free to reach out. Very happy to test your modules and provide regular data updates. And your information is safe with us. Okay, so talking about, that's probably my part for the Tandem, which we kind of using series connection to connect one cell on top of the other. And then what's next? Is there any alternative ways we can further push the efficiency beyond the limit? And besides, I guess we all done our physics classes in high school. So beyond the series connection, there's definitely a parallel connection. So this is kind of like a more advanced anti-reflection coating layer, where you just put an additional layer on top of the cell, and then you manipulate the incoming photons before it reach your silicon devices. So, and this is what we call the photon conversion. And regardless of photon conversion, there's generically two ways you can convert the photon. One is down conversion, and the other is up conversion. So down conversion, just by the name of it, you can guess, you just convert the high energy photons into lower energy photons. And theoretically, if you do a good job, you can push the efficiency limit by another 5%. And the other one is the up conversion. So up conversion is you just combine the near-infrared photons, where cannot be absorbed by silicon, combine multiple of them, and then convert them into one, like a usable, visible photons that can be absorbed by silicon. And again, if you can do a good job with your up conversion, you can further push the efficiency limit by another 7%. And what if we combine the up and down conversion? We almost can achieve almost the same efficiency limits with a 2D devices. So you can see the order limit for up and down conversion is almost the same with an order limit for 2-junction device. And that's what we've been doing with IcoSolar. So now let's have a look at the efficiency potential. As what I started in my talk, I said we love silicon. It's definitely an excellent material for the photovoltaic devices. So we wanted to maintain the potential of the silicon devices. And you can see for our DC, for our down conversion and up conversion devices, we are definitely getting the full potential of the silicon devices. But for the 2-junction and the 3-junction or the multi-junction devices, actually we rely a lot on the top subcells. And the silicon, which is the red part, only contributes a small portion of the overall efficiency. So here I just want to say the down conversion and up conversion is really an elegant way that we can further push the efficiency limits, and also we can get the full potential of silicon devices. And we are not competing with Tandem, because you can apply these layers on Tandem as well. Okay, so now after talking about the theoretical concepts, let's come to a bit more technical parts. I'll just take one material, for example, that we've been doing in our lab, that we are using quantum dots. So before we do the down conversion, we wanted to have a look at the downshifting for more immediate impact. So downshifting is like you just shift one high energy photons into one low energy photons, just a one-to-one shifting. And you can see by applying this downshifting approach, we actually can shift this harmful UV light, which our cells don't like, to more usable and more efficient visible lights. And here's what we've been doing in our lab. We are testing different materials. Here's just one example where we are using the nanoparticles. So we use the hot injection method to synthesize our nanoparticles and then mix it with the commercial polymer materials like EVAs or POE, and then using Dr. Blade method to apply to our devices. And you will form these amazing downshifting layers. And we can see efficiency enhancements between 1% to 2%, relatively. So these nanoparticles shows excellent optical properties. You can see it shows very strong absorption in the below 510 nanometer, and it also shows a very sharp and narrow emission peak in the visible. And there's one term we like to assess how efficient this down conversion process is. It's called photoluminescent quantum yield, PLQY. So it's very difficult to make your material having 100% PLQY, because that means for every 100 photons come in, you have 100 photons coming out. And we can successfully synthesize our material within 100% PLQY. And this material, literally, it can mix with all kinds of commercial polymers without any problem. We also tested the stability. So stability is great. So we've been leaving our materials in the ambient for months, and we can see it just retains at 100% PLQY for months. And we are still monitoring the performance. Okay, so as I said, we are doing this downshifting for a bit near-term impact, and for long-term, we are not satisfied with only 100% PLQY. We want to further push it to 200%. So that's why here's the concept of down conversion, where you can convert one incoming high energy photons into multiple lower energy photons. And theoretically, the PLQY can achieve 200%. And this is what we've been doing in our lab. So again, using the nanoparticles as an example. So without doping, as I showed you before, it shows this excellent optical performance. It's showing a very sharp emission peak in the visible. But with certain dopant, it actually has very strong emission peak in the near infrared, where silicon can also absorb very efficiently. So it's like you are converting one high energy UV photon into two lower energy infrared photons at 980 nanometers. We're successfully seeing this nice near infrared emission, and we are mirroring PLQY more than 100%. And we are on the pathway to further improve it towards 200%. And of course, this is just the beginning, because there's a lot more we can do. We need to looking for more stable materials, and we need to elegantly integrate it into our solar devices, and also looking at the stability and the techno-economic analysis. And with that, I'd like to acknowledge the support from our center and our funding agency, and of course, my amazing team who are behind all these good results. Thank you very much.